So I did this work with my co-first author, Yoje Lee from UIUC and other folks at Microsoft Research. And we are looking at new drone applications that enable timely analytics. All right, so drones have really taken off in the commercial industry sector of agriculture, energy, construction, and so on. And with timely analytics, what we mean is we want to make available actionable insights back to people on the site. This might include the drone pilot or any experts on the field. And this is not really possible to do right now in current systems, as I'll talk about later. But let me first show you 3 scenarios where we think timely analytics is really needed. And this is based on our analysis of relevant workloads from the commercial industry sector in the last 5 years. So drone pilot time is really important. They have to travel large distances to get to these remote regions. And what happens is if they can quickly fly the drone and get some low resolution images first, then they can look at anomalous regions and focus on an anomalous region with a second flight, and this time with high capacity cameras. So oftentimes there's a remote expert that is receiving some of these snippets from the edge, and that has a knowledge about the application, so they can give feedback to the pilot, and this can enable the pilot to focus on the right number of regions. And oftentimes there is a maintenance crew that is trailing the drone. So the drone is trying to find all the relevant regions that might need some inspection or some kind of maintenance. So as soon as they are found, maybe with the remote expert again, the engineering team can quickly go to those regions and then do the maintenance. And here we need to optimize both the drone pilot time as well as the engineering team's time. So in trying to support these scenarios, we ran into 2 main challenges. So challenge 1 is that the data generation rate at some of these edges is really high. We will be focusing on aerial drones that have downward facing cameras, then terrestrial drones, and instruments equipment such as tractors that have like cameras fit into them. So what happens is the data generation rate is very high, up to gigabytes per second or gigabytes per minute, and that's much larger than the speed of the network. And this really negates the possibility of analyzing these images in the cloud. So we cannot send all of these images to the cloud, and we don't really benefit from the high compute resources that are found in the cloud and maybe other streams such as historical data and other satellite imagery and so on. So the only thing that we can do here is we can extract the relevant snippets that are important for the application. Okay, and so we need to do some computation at the edge and minimize the amount of data that we have to send. So this brings us to challenge number 2, which is that to extract these snippets properly, we need to have a lot of compute resources at the edge. But at the edge, we have maybe just a single laptop and nothing more. So let's see why we need so much compute power. So first of all, to generate holistic insights, we need to look at like panoramic images or orthomosaics or 3D reconstructions. And we need to construct this, but this is actually very expensive. So just to, for example, stitch a couple of acres of land, it might take like a few minutes, and that's very expensive. If we were to look at each image in isolation, do some kind of frame by frame analysis, that is expensive too, because these frames have overlap to enable stitching. That just means we have so many frames to look at. And at the same time, because there is redundancy, the analysis is not that straightforward. And suppose we were able to get the final stitched image in no time at all, we still have to transmit this over the cloud, and that stitched image is like a few gigabytes in size anyways. So that's still very hard to send in time. So our system Visage tries to address these challenges. It is the first system that enables timely analytics within reasonable time frames. And one of the key contributions of Visage is that instead of creating a global stitched image that covers the entire surveyed region, we are going to construct individual localized stitched images around only the anomalies and some of the neighborhoods. So we'll create multiple of these depending on how many interesting regions there are. And by doing things this way, we will drastically reduce the amount of computation that is required to construct these images, because we don't have to look at all the frames. And we don't have to send a huge amount of data either, because the aggregated size of these localized stitched images is much lower than the entire global stitched image. So let me give you an overview of the architecture. So we need to model the relationship between the different frames and how much they overlap. And this will really help us in understanding what part of the region is being captured by the drone. And this can help us do some intelligent skipping of the frames so that we don't have to look at all of them. Next, once we find a frame that is covering an anomalous region, we need to quickly extract all the relevant frames that capture the same area, and so that we can start the stitching process. So we have a data structure that enables us to do exactly this. Then at the edge, we have to obviously send these localized stitched images to the cloud. And not everything in the image is equally important. Maybe some part is the sky or the soil, and that is not the anomalous region. So we have ways in which we can prioritize sending the proper amount of pixels to the cloud. And we do this progressively as well, which means we send the lowest resolution of the data possible first, and then we send we improve the quality of the bits over time. And then once these images are in the cloud, then they can be looked at by the expert, and then they can be sent back to the edge. Okay, so I'm going to give you a more detailed explanation of how we implement these techniques. So obviously we have established that we need to stitch, but we don't need to stitch everything. That's going to be very expensive. So how do we detect if a frame is actually important? So we use a domain-specific model, an application-specific model that will tell us, for example, that yes, this frame is capturing some anomalous data. And once we have found this, we will look for more anomalies, right? And to do that, the frames that are being streamed, some of them will be overlapping and will be capturing some of the same areas. So we prioritize the GPU time we have to look at frames that are exploring some unexplored areas that we haven't analyzed first. And we do this using our spatial database that tries to model which areas are being covered by the frames. Next, so we have established that stitching everywhere is going to be very slow. So suppose we find a frame that is looking at an anomaly. Okay, and now how can we extract all the relevant frames that are also covering the same region so that we can start the stitching process? So again, we look at the database. We have a database optimized query that can give us all the relevant frames that we need to do the stitching. And then we stitch those frames with higher priority. So some regions are again going to be more important than others. So we have like a hierarchy of priorities. And based on that, we are doing the stitching. And obviously localized stitching is very crucial because that gives the expert a holistic view of not just the anomaly, but the area surrounding the anomaly as well. Okay, so on a high level, what is happening is the drone is streaming the images to the edge, and the edge is then sending these localized stitched images to the cloud for analysis. And then at the end of the day, the insights are being made available to people on the site. So these stitched images can still be very large, up to hundreds of megabytes. And if we try to send all of these, it will take a lot of time. So what we do instead is we do some semantic segmentation of these images, and we find which segments are the most important for the application to receive. And we prioritize sending those pixels first. And even there, we send the lowest quality bits first and then improve the resolution of the data. So I'm going to show you a demo that will make this clear. So here is the localized neighborhood of around the anomaly, and we send the lowest resolution quality of the data first. Next, we will gradually improve the quality of the anomalous region. So suppose this is the anomalous region. And once this is there, we will improve the quality of the rest of the image. So you can see how this accelerates the analysis, because the expert can start giving feedback as soon as the important bits are there in the cloud. Okay, so I'm going to show you some experiments that show how our system works. So we have analyzed on a 5 terabyte data set over 500 plus drone surveys. And for all of the analysis on the edge, we just use a commodity laptop that has a single GPU and so on. And the uplink capacity is only 3 megabits per second, which is typical for these applications. So first, we will be measuring the fidelity of the data. The data that we send is based on local information about the frames that are present. So we measure the quality of the same region by comparing it with the same region in the global stitched image. And then we can do a pixel by pixel match and see how accurate we are. And we measure something called peak signal to noise ratio, and which is weighted towards the more anomalous regions. So in this graph, what I'm showing is on the x-axis, we have time, and on the y-axis, we are measuring how accurate the data is. The higher it is, the better, of course. So what we notice is Visage with existing encoding and decoding techniques achieves high quality in much less time. And we did a similar experiment with a different metric that is called weighted similarity. And here we also found that we reach high fidelity of the data in very less time with Visage compared to other systems. And then obviously what matters to the application is the application metrics like plant counting, fruit counting, or green cover using some NDVI analysis and so on. So what we are measuring in this experiment is, for example, how quickly can we reach the desired plant count, the actual plant count data with the elapsed time. And what you will notice is that when Visage is enabled, we reach the actual metric in much less time over, again, very low quality internet. And this compares very well to existing systems that can take hours to do the same thing. And next, I'm just going to give you an overview of the rest of the experiments. If you're more interested, please refer to the paper for more details. So as long as the network uplink is less than 15 megabits per second, and this includes 99% of edge deployments, Visage is going to be very beneficial in reducing the latency of generating the insights. And we start getting the first images from the site in as few as 10 minutes. And we get up to 40 decibels of data fidelity, which is considered very high in very early into the experiment. The median latency to get the first insight is 18 minutes. And it is 33 minutes for the 95% latency. And that's 200 times better compared to existing systems. And we do all of this again on just a single laptop. So I'll just summarize the results quickly. Visage improves application latency by really prioritizing the compute and the network resources on the most important bits of the images. And it does this all with a single laptop. What we are focusing right now is, can we include other streams such as satellite data or data from other sensors and static cameras to assist the drone pilot. Okay, so this concludes my talk.